Well, good morning, and welcome to lesson 4 of Civil Engineering 3372 Water Systems Design. The topic today is head loss models. So this will be a review of material that you had in your fluids mechanics classes. It'll probably come back to you pretty quick, or maybe never left. But over next few minutes, you should probably have no trouble refreshing your experience in those classes. I'm going to stall a little bit while any latecomers or people that are in apartment complexes that have their daily fire alarm get back into their apartments, or those that are on campus, whatever frustrations you're facing, give everybody a chance to get connected. And I will turn on the chat window because sometimes that's handy. And I will shrink that. So I have my camera turned off on purpose. It's not really necessary for today's lesson, and I've been having trouble with my webcam lately. I don't know if it's the manufacturer's way of telling me to buy another one or if something else is going on, but we'll do without. So that's 28. That's I'm expecting about 35 to 40, so I'll wait a little bit longer. There's 30. Hope everyone's having a great Thursday. The weather looks beautiful. I haven't been outdoors yet. My cat is joining us for the lecture by sleeping on the phone and part of the computer. Are you okay? He looks okay. And so any topics we get to that require the cat's input, he will get up and let us know what he thinks. He mostly thinks humans are pretty dumb, except when it comes time to get fed and groomed. We're useful for that. All right, that's pretty good stalling, so I think I will just go ahead and plunge forward. I just created on the blackboard the links to this lesson. For some reason I thought I had done it, but apparently I had not. And so if you go to the home page for the Blackboard class, nothing happens because the computer's determined that it doesn't want to work right now. There we go. And in the lesson collection, lesson 4, content links, and there's only one thing in there right now. So this will take us to the content server, and the title of today's lesson is Pipeline Head Loss Models. Not very much of a description, review of head loss models. The notes section is as usual. I've already done this, but I'll do that on video. Verified that link is active. Some hydraulics notes. So what I'm doing today is largely borrowed from this document, and you can read that on your own. Pages 10 to 26 of a book by Chin, which has a more intimate detail of the pipeline hydraulics. And back from when I was in school, the world was sepia, a whole chapter on closed conduit hydraulics. And this chapter is also, you actually will recognize some of the pictures. This chapter is also a good reading material to refresh your memory on these particular concepts. And we'll move on to the lesson notes. I'll start with part 1. And quickly go back here. None of these video links are active, so this never got pre-recorded, so today's recording will be the recording. So this is going to change 20 hours from now once all the videos are rendered. Alright, so Pipeline Hydraulics Part 1. Just some real brief introduction or refreshing the memory. Water, at least on our planet, moves from higher to lower energy following the path of least resistance, and we use a measure of energy called head, which is the energy per unit weight of a fluid. And to add energy to a system, we use a pump. If that fluid system happens to be a gas instead of liquid like water, then the pump gets a new name. It's called a compressor. The general purpose is to do the same thing. It's to add energy, and that allows water the capability of moving to a higher elevation or over some barrier, or if you push it through a nozzle, it could be used to cut things. The first flow characteristic to refresh our memory is water moves from high head to low head, unless there's a pump or other source of energy added to the flow system. The second concept is gravity flow, and this is where the energy for water to move is provided by elevation. So in gravity flow, change in elevation provides the required energy. The Los Angeles aqueduct, using that as an example, is technically a gravity flow system because Lake Owens, the Owens Valley, is several hundred feet greater in elevation than downtown Los Angeles at the Department of Water and Power, where the water comes into the basin. That's a gravity flow system. In theory, you don't have to add energy to it. You just have valves, and it does all the moving by itself. The contrast to that would be a pressure flow system. In that case, the change in pressure is what provides the required energy. Most real systems are a subtle combination of the two, but if for some reason we have to push water uphill to get to our end customer, that would generally be under the category of a pressure flow system. We would have a pump in the system. It adds a considerable amount of energy. Much of that energy would manifest itself as increased pressure in the pipeline at the lowest end, and then that would provide the energy for the water to move itself uphill and go on to a customer. The flow rate is an important concept, and usually in flow rate in water systems, we're referring to the volumetric rate of flow. How many liters per minute of water is passing a point, or how many cubic feet per second, or how many gallons per minute, whatever the volume unit is. If that volume unit is pre-multiplied by the water density, so if you see rho Q, for instance, that's a mass flow rate. That's also of certain importance, but relatively less common in day-to-day water system design principles. If we divide the flow rate by the cross-sectional velocity by the cross-sectional area that it's passing through, the result of that is called the mean section velocity. Here I have it written as V with a bar over the top, or just plain velocity would be pretty much understood that this is what you mean. So the velocity, when we talk about the velocity in a pipe, we're usually referring to this mean section velocity, unless we have flow profiled the pipe and we're talking about the velocity at particular locations relative to the center line of the pipe. And that has applications in things outside water system design. Now, moving water also creates or experiences friction and resistance, and that causes head loss along a flow path. So if we had an absolutely frictionless pipe, the only energy that the water would have to have is sufficient energy to handle the change in elevation. But in practical systems, it also has to have enough energy to overcome friction imposed by the system. The next concept from fluids that I want to refresh is the concept of continuity. And continuity is simply the expression that unless there is a source of water or a leak, that the flow rate, volumetric flow rate, is the same at two different locations in a water system. And how that becomes manifest is in this diagram here, where we have a large diameter pipe, in this case connecting to a small diameter pipe. The volumetric flow rate in the two must be the same by the principle of continuity or the conservation of mass. Therefore, the only way that the flow rate can be sustained in the two different parts is for the mean section velocity to adjust based on the cross-sectional area, which leads to what I have written up there as equation 2, that the area of cross-section 1 multiplied by the mean section velocity of cross-section 1 is equal to the area of cross-section 2 multiplied by the mean section velocity of cross-section 2. And you use that back in your fluid mechanics class in various problems to find different velocities, usually in combination with the momentum equation, to explain how particular fluid systems would behave. If we have a junction, which is no different than a prior picture, it just has more parts. In water distribution systems, junctions, the word junction or node are used pretty much interchangeably, although in theory they're quite different things. But think from modeling perspective, we have this junction. And in this drawing there are 3 pipes coming to a junction, and then there's this fraction of water that's exiting from the junction, leaving the pipeline system going somewhere. And in this case, I have that labeled as an external demand. So the principle of continuity at a junction is that all the inflows equal all the outflows. And in this drawing, I have Q1 to the left pointing in towards the junction, Q2 at the top leaving the junction, Q3 at the bottom also leaving the junction, and by convention demand is positive leaving a junction. So if I were to apply the principle of conservation of mass or continuity, the continuity equation for that junction in this picture is Q1 minus Q2 minus Q3 minus demand equals 0. So all that is a conservation of mass statement. A somewhat more common way of writing it would probably be Q1 minus Q2 minus Q3 equals demand. Keep in mind that by convention, demand is positive leaving a junction. And finally, I want to refresh your memory on our friend the energy equation. And it's written here, and I'll read it to you slowly in a second. But the energy equation, you either learn this in fluids as the energy equation, or if you took fluid mechanics elsewhere, it was called the modified Bernoulli equation. Those are both correct ways to refer to this expression. And what it does is it relates the total dynamic head at 2 points on a flow system, in this case a pipeline system, accounting for frictional losses, in this case any added head from a pump, and it looks like I have a turbine in it. So the energy equation is written here is moving from location 1 to location 2. So it's implicit that flow is from 1 to 2. If that's not the case, the signs of some components are changed. It says that that P1 over rho g, which is the pressure head at location 1, plus v1 squared over 2g, which is the velocity head at location 1. And there's this alpha term here, which is a energy correction coefficient. In practice, we usually take it as unity. It's not something that's terribly easy to measure in the whole scheme of things, but it ranges between 1 and 2 in observation. So we usually just use 1 and call it good. Plus the elevation head, z1. We'll ignore the h sub p for the moment, is equal to the pressure head at location 2, the velocity head at location 2, and the elevation head at location 2, plus the head loss term, which is out here to the rightmost where the cursor is circling right now. I have to do it for a while because at 5 frames a second it takes a while to capture things. So this group of 3 terms is also referred to as the total head at position 1. And this group of 3 terms, after the equal sign, is the total head at position 2. And we have a few other terms in here. We have h sub p, which is any added head supplied by a pump between location 1 and location 2. And I have h sub t, which is the term that refers to any head extracted by a turbine between location 1 and location 2. So if there's no turbines in a system of interest, this term is 0. And if there's no pump, that term is 0. And then the head loss term is replaced by whatever head loss model we're using appropriate to the study at hand. So here's a diagram of the energy equation in a case where there's a reservoir number 1 that's at lower elevation than reservoir number 2, and the water is connected from 1 to 2 through a pipeline and pump system. And so in this instance, assume the system is already primed, so the whole thing is already full of water, and the pump is running, and so water's moving from 1 to 2. Well, to get from this point in the pipe to the suction side of the pump, the water's moving, and so it's losing energy due to friction along the way. So this energy line, or energy grade line, is depicting that. And then the sum of the elevation head plus the pressure head is the hydraulic grade line. It's also declining as we move towards the pump. Then when we get to the pump, it adds energy. It adds this huge amount of energy, this red segment here. And so now our energy grade line is located at this point, and it declines as it moves towards the reservoir number 2. Now the water is actually flowing in the pipe in these purple sections. And so the head loss from position 1 to 2 includes the head loss in this part of the pipe system and that part of the pipe system. And the added head of the pump is shown right here as the red line segment. And the total head at 1 and the total head at 2 are the result of the sum of these 3 terms added together at each of the locations. So that's the review of the energy equation that you would have had in fluid mechanics. And other than the picture explaining things, that's about all we have here, except that it's useful to know how to draw energy lines and hydraulic grade lines. So the energy loss, what I have located as the purple lines in the prior figure. It's influenced by both hydraulic and geometric properties of the system. The hydraulic properties that contribute to energy loss, or routinely called head loss, are the roughness of the material that the pipe's made out of. So all other things being equal, one would expect smooth pipes to have less energy loss than a rough pipe. Any intervening components such as valves, bends, T's, and other fittings between points 1 and 2, and oddly enough, the overall operating pressure, or operating head, if you will. The geometric properties that affect the loss behavior are how long it is. So a 50-foot garden hose has much less head loss than a 500-foot garden hose. And also the cross-section, the shape and the area of the conduit itself. So pipes are usually round, but they don't have to be. We saw, we didn't see square ducts. I retract that statement. We had a round hole in a square piece of wood. That's not a square pipe. The cross-section shape plays a role. And if you recall, in your fluid mechanics class, you should have been introduced to the concept of hydraulic grade line. And that's a line that just represents the surface of water flowing in a partially full pipe, or even a full pipe. The way to visualize it is if you had a conduit and there was water in it, the hydraulic grade line at any point would be the sum of the elevation head and the pressure head for that flow system. So in this diagram, it's coming up to that point in this vertical pipe that's connected to the pipeline. In this point, it's coming up to here, and then you would figure out where all those points were and draw a line connecting them, and that becomes the hydraulic grade line. It's how high water would rise in the system if we don't consider the velocity component. The energy grade line is the hydraulic grade line plus the velocity head term. So in this picture, it's depicting a pitot tube that's introduced in the system, turns, and then faces into the flow, and that energy, the velocity component adds a little extra energy, and so the difference between the two is called the velocity head. Hydraulic grade lines are important in distribution system design to some extent. The energy grade line is more important, and they're both very important in drainage system design. Because if this picture right here were, for example, representing a sewer system, we'd have a problem because we're operating it under pressure, but let's ignore that for a moment. And the hydraulic grade line plots above the land surface elevation. That would generally be problematic, because what it would mean if there were any way for water to get out of the sewer system, it would, and it would get out and it would flow all over the land and flood things with nasty water, and that would be undesirable. It would cause us to have to work on a resume real quick, or possibly move to a country without an extradition treaty. The energy grade line, as I previously stated, is the line that represents the elevation of energy head of water flowing in a conduit. It's the sum of the elevation head, the pressure head, and the velocity head of the location. And it should lie above the hydraulic grade line at a distance equal to the velocity head. And one can use plots of energy grade lines and hydraulic grade lines to actually infer what's in a water system, whether there are pumps or turbines or diffusers or confusers there. And you had that in fluid mechanics. The classic fluid mechanics is, here's a hydraulic system, here's the energy grade line, what's between points A and B? And you have to determine if it's a valve or a reduced pipe size or a turbine or something. And here's an example of that very case, a turbine or something. So we have a upstream reservoir. In this case, we're told there's a turbine. We can see it's right there. It's a turbine right on it. So the water flows down this penstock, which is the fancy name for a pipe that carries water to a turbine. And then it goes to the turbine, does its spinny thing, makes electricity, and then it is wasted from the turbine into, this would be called the tailwater. So headwater up here, tailwater. And yeah, we can build all the parts of a small animal with this diagram. If we were to look at any point along this line, this picture is taking the top of the tailwater pool as its reference elevation, and we would move up to a point on the flow system. That gives us our elevation head. So over here at this side, the elevation head is that distance. Over here it's this distance, and when we get really close, it's a very small distance, and that small distance right here. If we were to punch a hole in this line and put a vertical pipe all the way up to the moon, the water would rise in that vertical pipe up to that height, the P over gamma, or the pressure head term. And if we put a pitot tube, it would rise in the pitot tube a little bit further, this V squared over 2G part. So a fair question is, why we design it with V squared over 2G so small? These are usually large diameter pipes. The reason being is that the head loss is proportional to the velocity head. So if the velocity head is big, we get a lot of head loss. And we want to take all this energy that's up here contained in this reservoir and get it down to the turbine with as little head loss as we can conceivably get away with. And the head loss in this diagram is manifest by the slope of this line. So if we let the velocities get too high, this line has a steeper slope, and it might plot something like that, and we won't have as much head available to be extracted. So the turbine extracts this amount of head, and then there's a little bit left over to get everything out to the tailwater, and that's the hydraulic grade line and an energy grade line in the turbine system. So I included this diagram just to explain hydraulic grade line and energy grade line. There is good description on both. No, not in Chin. Well, maybe there is in Chin, but in this chapter 5 of Robertson Cassidy, they talk about, I think they do hydraulic grade lines in here. I could be a liar. Do it enough. I know that picture came from there. It has a whole 3 pages on hydraulic grade lines, energy grade lines, that I would recommend you read. It also talks about cases where you get negative pressures in systems. We try to avoid that. If it gets too negative, the water will phase change from liquid to gas, and the system fails to work. And if it gets even more too negative, there's actually enough air pressure to crush it. And that is a bad thing. Letting it load. And here. So we've seen our energy equation already. This is just to refresh it. And now we'll look at applying it. So that was your refresher. Let's imagine, for the sake of discussion, that we were presented with this problem. So we have 2 reservoirs connected to one another through a 2-mile-long, 2-foot diameter pipeline, and we're told that the pool elevation difference is 20 feet, and we want to estimate the discharge between the 2 reservoirs. So the energy equation, if we were to apply it, we would come up with the total head at reservoir 1, there's no pump in it, equals the total head at reservoir 2, plus the head loss from 1 to 2. Well, the total head at reservoir 1, we don't know what it is, and we don't know what the total head at reservoir 2 is, but if we take this term and subtract it from the left side, we get H1 minus H2, which in the picture we're told is 20 feet. And then we have head loss is equal to, someone did some work for us, told us it's equal to 0.136 multiplied by the length, multiplied by Q squared, divided by pi squared G d to the 5th power. And that head loss term is a particular head loss model. It happens to be the DARCY-WEISBACH model, but it's a model of head loss. And so the question is, can we estimate the discharge between the 2 reservoirs with just the information on the picture? So the answer is probably yes, because otherwise I wouldn't have put it there. We know the head loss is 20 feet from the drawing. So we have 20 feet equals 0.136 times the length. Do we know the length? Yes, it's given as 2 miles. Q squared, we don't know that. Divided by pi squared, we can look up pi in the bakery catalog and square it. G, we can look up in the gravitational acceleration catalog. And the diameter is given as 2 feet. We can certainly raise 2 to the 5th power. So we know the entire denominator. We know the value for L. The only unknown in this expression is Q. So yes, we could estimate the discharge between the two reservoirs. And if we do that, I think we'll get like 11 cubic feet per second. So that's kind of the easiest application of the energy equation. We applied a head loss model in that the one we applied was Darcy-WEISBACH. There's 2 others, Williams, Chesney Manning. Oh, there's probably more than 2 others, but these 3 are the most common ones. And back in your fluid mechanics class, you were probably introduced to the Moody chart. You may have been introduced to the Jane equations. Ah, damn it. Hello? Yeah. Okay, thank you. Bye-bye. And the other type of losses are minor losses, and we'll get to those shortly. So returning to our energy equation, we're going to examine the orange part right here, head loss models. So the first head loss model we can examine is the Darcy-WEISBACH model for pipeline head losses. And you would have had this in fluid mechanics, and the model looks like this equation. The head loss due to friction is equal to a friction factor multiplied by the ratio of length to diameter for the pipe multiplied by the velocity head in the pipe. The frictional loss model is proportional to the length of the pipe, proportional to the square of velocity, and inversely proportional to the cross-sectional area. The loss coefficient F depends on the Reynolds number and the roughness height. So we have a fluid flow property influence and a pipe material property influence. So if we examine this equation and suppose that that is an effective model of friction in a pipeline system, we can learn some things just looking at it. If the faster water moves, the energy loss goes up to the square of that speed. So if we're moving water at 1 unit per second, we have 1 unit of head loss. If we double it to 2 units, then we have 4 units of head loss. So we want to keep water moving relatively slow, but it has to be fast enough to move other things like solids in it, at least for drainage, but not, and we don't want it to be too fast. We also see that as our pipelines get longer and longer, the head loss increases. Since the purpose of them is to move water from point A to point B, we don't have a whole lot of degrees of freedom on the overall length. I mean, if we can cut diagonals instead of having to follow street grids, there's some advantage to that, but it's not a whole lot. But we also see if we get the diameter bigger, we can reduce the head loss. And a consequence of bigger diameter is also going to be smaller velocity. So keep that in mind that we do a lot of hydraulic control on diameter and then the associated reduction in velocity with greater diameter. So this will be a quick review of the Moody chart in water system design, the Moody chart is useful but not terribly practical for a complex system. So it was a tool to estimate the friction factor in the Darcy-Weisbach head loss model and is used for the pipe loss component of friction. So we haven't talked about any of the fitting losses yet. So there's what the Moody chart looks like, and it's a collection of curves where the cursor is moving, and each curve corresponds to a relative roughness, which is the material roughness height divided by the conduit diameter. Over on this part, if we know that the flow is laminar, the friction factor is by definition 64 over the Reynolds number, but at a Reynolds number between 2 and 3,000, this model becomes meaningless and the friction factors jump up to one of these lines. There's a fully rough dividing line here, which corresponds to the case where each of these roughness ratio lines becomes horizontal. Anything in this region to the right of the fully rough flow is entirely controlled by the pipe material. In the transition zone, we are a balance between the two. And when we get onto the smooth line down here, the friction factor is entirely a function of Reynolds number. So 3 examples of the use of the Moody chart. We'll go through these relatively quickly. The classic one from Moody's original 1948 paper is to find the head loss given discharge, diameter, and roughness height. And this is what the chart was designed for, so these are pretty straightforward. You would calculate the Reynolds number from the discharge and the pipe diameter, then compute the roughness ratio from tabulated roughness heights for the pipe material, and then the friction factor would be recovered directly from the Moody chart. So as an example, suppose we have oil with a specific gravity of 0.9, a viscosity of 3 parts in 100,000 feet squared per second, flowing in a 2,000 foot long, 6-inch diameter cast iron pipe at a rate of 1 cubic feet per second, and the pipe slopes upward at 5 degrees in the direction of flow. So in the 1940s, that was how slopes were presented, at least in that paper. Nowadays, we would use, probably represent slopes as percent. But anyway, it's sloped uphill in the flow direction. So we're asked to estimate the head loss in the pipe and estimate the pressure drop from points 1 to 2. So here's a sketch of it, not much of a sketch, but there's a pipe there with a 5-degree angle, 2,000 feet long, and it has a flow rate of Q in it. So if we apply the energy equation to that situation, it would be P1 over gamma plus Z1 equals P2 over gamma plus Z2 plus head loss. The velocity head at positions 1 and 2 didn't disappear, but because the pipe has a constant diameter, they're going to be the same at each point, so they cancel. So we rearrange that equation to isolate the head loss, and we find that P1 over gamma minus P2 over gamma, which is the change in pressure, plus Z1 minus Z2, which is the change in elevation, gives the head loss. And so finally, the head loss using the Darcy-Weisbach model is evaluated as follows. The Reynolds number is velocity times diameter divided by kinematic viscosity. Or in this instance, it's 4 times 1 cubic feet per second times 0.5 feet. So divided by pi divided by 0.5 feet squared. So the 4 times 1 cubic feet per second divided by pi divided by 0.5 squared is the flow rate Q divided by the area, which returns a velocity. Then we divide that result by 0.00003 square feet per second to get a Reynolds number of about 85,000. The roughness height we look up in the Moody chart, either in the document or on the internet, based on the material. And in this instance, it's cast iron, and it's 0.00085 feet. So we take that number and we divide it by the ½ foot diameter of the pipe to get a roughness ratio of 0.0017. And that's all we need. We enter with the Reynolds number of 87,000. We find the 0.0017 roughness ratio curve, which I have drawn here as a teal line, blue wing teal. And then at the intersection, we read over to the left to get the friction factor of 0.024. And that would be used in subsequent calculations related to that pipe. And then we would complete the analysis by using the Darcy-WEISBACH equation to estimate head loss. So it's about 38.6 feet of head loss in that system. And then to compute the pressure drop, we would observe that the change in pressure is equal to the specific weight of water multiplied by the head loss plus the elevation change. So we get a pressure change of almost 12,000 pounds per square foot, or about 83 pounds per square inch. And so the oil pressure has to be 83 pounds per square inch greater at the lower elevation for the oil to rise uphill. So there's 83 psi greater pressure at location 1 than there is at 2. If that's the case, the oil will move uphill. This 0.9 here is the specific weight of oil, so I'm using the specific weight of water and adjusting it for the oil. Second application of Moody chart is discharge given head loss, diameter, and material. This one requires an iterative approach if we're going to use a chart. So we would apply Darcy-WEISBACH directly, and we have head loss is equal to 40 feet because it's given. And we would compute the roughness height ratio, also from given information, as 0.0036. And then in the olden days, we'd build a table of computations, something like this. We would guess a discharge, calculate a Reynolds number, use that Reynolds number and this roughness height to look up a friction factor, and then calculate a head loss based on that friction factor. When the head loss that we guess gets somewhat close to the head loss we have to work with, we found an answer. So in this first instance, 0.001 discharge produces very little head loss, and so we're not matching the hydraulic requirements of the system. The head loss is lower than that's what's available, so we increase the value of discharge. Do it again. Here we have 12, I think these are feet of head loss. It's still less than 40, so increase it again. We now have 31 feet of head loss, and you'll notice the friction factor is changing. Each one of these rows, we're looking up the friction factor in the Moody chart. And at 0.009, we've probably hit the point where we can't read differences in the chart anymore. Any entry we come up with, we're going to keep getting the same friction factor. So here we get 37.9, 38 feet of head loss, which is probably as close as we can get using the chart. And so we would report that the discharge is around 0.009 cubic feet per second. The last one, the actual design question, is what diameter should we use if we want to carry water at 3 cubic feet per second through a 600-foot pipe. It drops 60 feet in the flow direction, and we want to control the pressure drop to be within 6 feet of head. So we sketch the situation, apply the energy equation. The velocity head terms appear to disappear, but they really just cancel. And the resulting head loss equation is this creature here. And what we want to solve for is to find the value of D that satisfies that equation, bearing in mind that the friction factor changes with each value of D. And so here's a computation table set up that works on D. So if we guess a value for diameter, once we know that, we can compute a Reynolds number. We can also compute a roughness ratio. We use that Reynolds number, that roughness ratio, look up in the Moody chart this value of friction factor, 0.018, and the computed head loss divided by that friction factor is listed here, which would result in a computed head loss for the system of 2,500 feet of head, which is a wee bit bigger than 66, and so that's probably not a correct answer. We can increase our diameter, repeat the calculations, repeat the chart lookup, and we get 69 feet of head. So that's getting pretty close. We increase the diameter a teensy bit, 5%, and we calculate this particular Reynolds number, that roughness ratio, and this friction factor by table lookup. You notice they didn't change because we can't visually resolve them anymore in the chart, and get 63 feet of head loss. And so the correct diameter after 3 tries is somewhere between 6 and 7 inches. And in a hydraulic system, we would probably opt for the larger diameter. And it turns out that commercially available 7-inch pipe indeed exists. It's unusual, but you can buy it at Pipes R Us. And so that size could be specified in this situation. So in the 1970s, a set of researchers decided that that Moody chart was a pain in the butt. And so they came up with an alternative, which are a set of regression equations that were built using the same data as was used to create the Moody chart. And I have the 2 of them listed here. They're collectively called the Swamy-Jain equations, or just the Jain equations for short. It's kind of an irony because Swamy was the graduate student that did the work. Jain was the professor that the equations are remembered for. So they should be called the Swamy equations, but that's life. Unfortunately, not. Anyway, I'll shut up on that. Swamy-Jain equations. If you say that in hydraulic context, most people that are knowledgeable will think that these are what you mean. So there's one that calculates discharge given diameter, head loss, length, roughness height, and viscosity. And actually this H sub F divided by L happens to be the slope of the energy grade line. Sometimes that is how these are referred to. And then here's another one for diameter. It's the same information, it's just rearranged considerably. This will give us the ability to compute diameter given desired discharge, desired head loss, desired length, roughness height, so that would be desired material, viscosity, desired liquid, and compute the diameter for us directly. So as equations, those look pretty simple, but if you were to do those on your hand calculator, I would imagine that most folks, certainly I do, find this to be not simple at all. There's too many buttons to press. It's really easy to make a mistake. So what we would probably want to do is put them into some sort of computational tool. So that I have one already built that implements these notebooks. Well, actually, let's go look at this Jupyter Lab notebook, because future classes are going to have to know what that is. So that should be, actually I hope this actually works. I may have it turned off. So in future versions of the class that you're all in, there would be some time spent on this. But here's the equation we're trying to solve. So we build a prototype function. So that right there is script to evaluate that equation given pipe diameter, pipe length, roughness, viscosity, gravity, and head loss. And then a bit of an interface engine is useful. And let's go ahead and enter our prior problem, which was a 2-foot diameter pipe. It was 2 miles long. Roughness height, I think that was the roughness height for cast iron pipe. Trying to do this from memory for kinematic viscosity in so we had 20 feet of head, and is it actually running? Oh, it didn't run. Oh, okay, so now we've got the input and we'll actually do the calculations, and it doesn't work. My bad. Let's try it now. There we go. So it gives us a discharge of 19 cubic feet per second for these inputs. I don't even know if those are right. But another way is have that already coded online, and so we can look at that. And here we have a web-based calculator to compute discharge in a pressure conduit using the Swami-Jain approximation. So we'll select that, and our life is easier. Let's enter the same values and see if we get the same answer. So 2.0, 10,560. Better put in the same numbers, I'll get different answers. Roughness height, 8.5 times 10 to the minus 5. Let me copy that. Paste that. Kinematic. Get out of the way! All right, so our last one was 19. Let's see what this one does. And this produces 13.7 cubic feet per second. And I am not going to diagnose why they're different. One of them has different, oh, there we go, 10,000. I can't imagine 8 feet matters that much. But the one on the server I'm much more trusting of. So, or you can make your own. You could do it in a spreadsheet, for instance. And I believe there's actually a spreadsheet example. The next head loss model is the Hayes and Williams model. Now this one's pretty interesting because it appears in the water code as the preferred model, at least in the Texas code. Not necessarily because it's better, and it doesn't explicitly state Hayes and Williams. What it does state is it gives some suggested Hayes and Williams loss coefficients, so by implication it's the Hayes and Williams model. And this one's pretty similar, doesn't look it, but it is. So it has a coefficient, length, inverse diameter, velocity, roughness term raised to a power. So in the case of Hayes and Williams, the frictional loss is proportional to length, proportional to velocity to the 1.8 power, so almost proportional to velocity squared, so not much difference there. Inversely proportional to cross-sectional area, but the loss coefficient now only depends on pipe material and finish, and it's only valid for turbulent flow, and it's only valid for water. So the Hayes and Williams applied to non-water is incorrect application, and the Hayes and Williams applied to laminar flow, which is admittedly uncommon, is also incorrect. It's fairly simple to use. Again, the simple equation on a hand calculator is not that simple because there's a lot of opportunities to put the numbers in wrong. This value 3.02 changes depending on whether we're in US customary or SI units. And we look up the Hayes and Williams C factors in tables that look something like this. So here is an excerpt from www.engineeringtoolbox.com Hayes and Williams coefficient. And this is not what you get if you take that URL. I took the data there and retypeset it. But for instance, if we have a pipe made out of glass, the Hayes and Williams coefficient is 130. And this is how it's determined. There's no viscosity, so to speak. It's already been incorporated into the loss coefficient. And you'll see as the numbers get smaller, the loss actually increases. So a new pipe has a high Hayes and Williams coefficient, 130, but after 40 years and it's all clogged, it's dropped here in this case to 64. So keep in mind that as in the Hayes and Williams model, the value of the loss coefficient goes down for increasing friction, which is opposite of friction factor. So here's a simple example incorporating it. Estimate the head loss in a 72-inch, 10,000 foot long steel pipe carrying water at 200 cubic feet per second using the Hayes and Williams formula. So we would look at steel, and let's see if we have steel in here. Steel somewhere in the 110 to 90. Since we're good engineers and can't make a decision, we'll just use the middle value. We'll estimate it as 100. Hayes and Williams value of 100. Once that's done, the head loss is pretty straightforward. The coefficient for US customary multiplied by the length, diameter to the minus 1.167. Then convert the discharge into velocity. So 4 times 200 cubic feet per second divided by pi, 6 feet quantity squared, divided by the Hazen-Williams coefficient of 100, raise everything to the 1.85 power to get the 28 feet of head loss. The Hazen-Williams formula is often presented as a velocity equation, and it uses the hydraulic radius instead of the diameter. So here's a common way of representing it as velocity. So we have the Hazen-Williams coefficient, we have this radius to the 0.63 power, and a slope of the energy grade line to the 0.54 power. The hydraulic radius is defined as the ratio of cross-sectional flow area to wetted perimeter. And for a circular pipe that's full, the hydraulic radius is 1/4 the geometric diameter. So here's the perimeter, which is pi times the diameter. And the cross-sectional area is pi d squared over 4. We put those two into the hydraulic radius equation, divide out the common terms, and what's left is diameter over 4. That statement becomes false when the circular pipe is not full all the way complete. If there's any free surface, this is no longer true. You actually have to calculate the hydraulic radius. The last common head loss model is the Chezy-Manning formula. And it's not common to see it presented as a head loss formula, namely because it doesn't get used like that very often. But here it is, rearranged into the head loss structure. And if we examine it, we see that the head loss is equal to the length multiplied by the roughness coefficient n squared multiplied by velocity squared divided by 2.22 times the hydraulic radius raised to the 4/3 power. So that's literally Manning's equation, probably US customary, rearranged as a head loss. So the head loss is the slope of the energy grade line. So that would be the slope term in the conventional Manning's equation that you may be familiar with. What we learn by examining it is that the loss is proportional to the length, the square of velocity, inversely proportional to the cross-sectional area, in this case manifested as the hydraulic radius, and the loss coefficient depends on the material and the finish. And we look up the loss coefficient in tables, much like the Hazen-Williams method, except in different tables. Let's take a visit back here to the class server. So Manning's in. Good, it's active. So here's what Manning's in tables look like. So let's just pick well-built earth. No, I think I actually want to use. I may not have pipes here. I don't actually have them for pipes. There's similar pull-down information for a pipe. Let's just pick a smooth metal pipe. Manning's N for that would be 0.01. So this online lookup is available, but there's plenty of tables on the internet for using the Chezy-Manning's formula for head loss. There's also a Hazen-Williams head loss calculator here. We can actually repeat the example that was in the lesson. Let's do that just to be complete. So we'll redo that example. So it's 10,000 feet of pipe. (200 cubic feet per second of flow). (6 feet of diameter). And the loss coefficient is 100, and all it's going to do is evaluate this formula right up here. Let's see if I'm U.S. customary units, and the coefficient is 1.318. Okay, hit that, and it produces 27 feet of head loss, and doing it essentially by hand we get 28 feet. So those are, for all practical purposes, identical. The next topic is for review is the concept of minor losses or fitting losses. So fittings, joints, elbows, inlets, outlets, etc. cause additional head losses. And they have the name minor loss not because of the magnitude, because the magnitude of the loss can be quite substantial, but because they occur over short distances. And the typical or the most common loss model I'm familiar with is a velocity proportional model where there's the minor loss is equal to some loss coefficient multiplied by the velocity head in that fitting, joint, elbow, inlet, outlet, etc. If it's a fitting that changes diameter, so maybe it's a reducer, so it's taking a 4-inch pipe to a 2-inch pipe, the velocity head you use is in the smaller diameter, the larger value of velocity head. Because the fitting losses are one of the things, at least in design, that we want to intentionally overestimate them if there's a choice, so that we don't design and build a system that has more head loss than we anticipate. The fitting loss coefficients also appear in tables, and they look something like that. And so here's one that says that a T fitting, so that's one pipe that connects to two others. Flange, that's a type of connection. For the inline flow portion, the loss coefficient is 0.2, and if it's threaded, it's 0.9, and so on. So there's thousands of fittings. These tables, if they were complete, and they went as far as to indicate the manufacturer of the particular fitting, they could be hundreds of thousands of lines long. Here's an example of a fitting loss. Suppose we have a valve that has a nominal diameter of 8 centimeters, a known loss coefficient of 3.2, and it's put into a flow where there's a flow rate of 0.04 meters cubed per second, and we want to determine the pressure drop across that valve. While it wouldn't be a great idea, you could conceivably use a valve like that to determine flow rate. So we'd have to calibrate it for different valve settings and pressure drops. So let's just say we want to find the pressure drop. So we find the head loss across the valve. KV squared over 2G equals 3.2. That's given in the problem statement. Multiplied by the velocity squared. We compute the velocity from the given flow rate. 4 times 0.4 divided by pi over 0.08 quantity squared. We square that thing, so that's velocity squared. Divide that by 2, divide that by 9.8, the gravitational acceleration constant, for a head loss of 10.3 meters. Next, we want to convert that 10.3 meters into an equivalent pressure drop, and we do that by multiplying the head loss by the specific weight of water. And so that would be 9,800 newtons per meter cubed times 10.3 meters, which comes out to be 101,321 pascals, or 101.3 kilopascals, about 1 atmosphere, interestingly enough. So an 8 centimeter, so that's a little under 4 inch, somewhere between 3 and 4 inch diameter, carrying 0.04 cubic meters per second, produces almost 1 atmosphere of pressure loss. So that's an example of a minor loss coefficient. How all that plays into a hydraulic system design and analysis is, here we have an orange pipe here and here, and we can compute or at least prepare evaluation expressions for the pipeline head loss in these two orange pipes. Those would be the F L over D V squared over 2G. And so this length would be the length of part 1 plus the length of part 2. So this first pipe and the second pipe would be the pipeline head losses. And then we'd have to add in the minor losses if we are choosing to consider them. And the minor losses here would be a loss associated with the inlet at this location, this bend. We usually don't consider losses across a pump because the pump is adding energy. And then we have an exit loss here. We would add those three plus these two for the total loss model that goes into this orange circle in the energy equation. Huh. We may be done. I thought I'd done all this already. This is very frustrating. Oh yeah, this is a source file. Okay, we did all that. That's it. All right, I stand corrected. There is only 2 useful parts to the lecture. So I believe we are done for today, except let's look at some spreadsheets. So here's some example problems using Excel spreadsheets. Let's see if this one. So there's the 2 reservoir problem that I did while talking to y'all. And actually this goes through part of the gory details involved. I believe we have what we need for head loss models. So that constitutes the review. So our next lesson coming up is pipeline hydraulics, which apparently is not uploaded to the server yet. So I will conclude the lesson with just a quick review. We've looked at design guidelines. We spent last time on demand estimation, and today we reviewed our fluid mechanics. The key points for today are the head loss models, DARCY-WEISBACH and Hayes and Williams, which are by far the more common of the 3 for use in water systems. And Hayes and Williams is probably the most common, at least throughout the United States. The loss models generally need to include minor losses. If it's a single path pipeline system, it's pretty straightforward to do it by hand as opposed to having to use some software. And actually that reminds me of something. I'll probably work an example next Tuesday to reinforce these ideas. And it'll be using I'll probably use the web calculator to make my calculations easier. So in terms of review or preparation for the upcoming weekend, there's not much to do except to work on the exercise set 2 unless it's already due in exercise set 3. They're pretty straightforward. We've discussed all we need for that. And we'll be moving on to some more hydraulic exercises soon. I will be creating a quiz, and I will, if I post it, I'll send an email, but it won't be due on short notice. There'll be at least a week from when I get it posted to when it would have to be due, because I want you to have sufficient time to work on it. And I'll remember on quizzes, I'm trying to remember to program them to allow multiple attempts, at least 2, so that if you run through the quiz once and it doesn't work out, you at least get another shot at it. And that's all I really have for today. Are there any questions? I hope that you can access the exercises. The videos take me a while to process. They'll be there at least by tomorrow, if not by later tonight. The video capture software has to re-render the video. I do a little bit of editing and put some annotations in it. It takes an ungodly amount of time. I don't have to do much. I mean, mostly I'm just letting the graphics processing unit do its thing, but it kind of locks up the computer for me for half a day. So I beg for patience on the video uploads because it takes a while to prepare them. If there are any questions, now is a good time to ask. Either is there a date for the midterm exam in the 2 reports? Yes, I just don't know what it is yet. It'll get programmed into Blackboard and proceed from there. The first exam is not anytime soon, so I'm going to just ask you not to worry about that just yet. And it's going to be online, much like a homework assignment, so there'll be plenty of time to do it at your leisure. And my usual methodology is to be sure that you have one weekend that the exam is not due. You have a weekend between when the exam becomes available and when it's due to give you plenty of time. So I want to check I'm going to check the syllabus. That's why I'm moving here now. So if there's an exam, it's going to be, it'll either be mid-month, so that the logical places, Matthew, for an exam to occur is right about here or just before here. So that's one logical breakpoint for an exam. The second logical breakpoint for an exam is just before here. And then the final exam is going to happen. So whether we have 2 or 1 midterm kind of depends on my progress as we work through this schedule. My preference is 2 midterms because it's actually, I can make each one shorter, and that seems to be beneficial, certainly for me to grade them and possibly for you to take them. So that's my inclination, is the first exam will be somewhere, it'll either be somewhere around the 20th of September, although I'm kind of tending to the lazy side, I might push that later into September. So you've got at least 20 days before it is going to happen. And it would be online, and I normally do them historically as a combination of a quiz type and a file upload type of questioning process. It's possible in Moodle to program a quiz that has uploaded questions, or where you upload answers, and I'm sure it's the same in Blackboard. I just haven't had time yet to figure out how to do that. And I also have to kind of test them. which sometimes I don't do a good enough job of testing the tests before I put them out there. Okay, for the 2 reports, the first report will be due early October, and the second one is pretty much due at the end of the class. And that should give you the guidance I have. Are there any other questions? That was a good question, Matthew. A long answer. You asked what time it is, told you how to build a watch. Okay, if there's no questions, I'm looking at the clock. I should have ended 1 minute ago. So I'm going to go ahead and terminate the call. If you have other questions, you can certainly send emails. And with that, I want you all to have a great weekend. Be careful this weekend. It's Labor Day weekend, so I think you don't have school on Monday. We were supposed to do a stay safe training video. I'm sure you probably got email from the university on that. All it's going to do is tell you to be safe, and I'll do the same thing. Have a good Labor Day weekend. Be careful and try not to get infected. Other than that, I will see you all next Tuesday. Bye-bye. Okay.